Hi everyone, I'm Dr. Munji, and today we're going to cover axial stress. So an outline for today's session, we're going to review stress and strain, which I have talked about in another video as well. We're going to go over elastic deformation of an axially loaded member and go over just a little bit of a theoretical derivation, nothing too heavy, just something to refresh your memory and help you kind of remember how we got that axial stress formula. We're going to go over an example problem, and then I'm going to leave you with a practice problem to try on your own to make sure that you are able to understand everything from this video. All right, so let's start with remembering a few things about axially loaded bars and the elastic deformation of an axially loaded bar. So the first important thing we have to remember is called Hooke's law, right? So let's go ahead and come here. And let's write down the formula for Hooke's law. We have F is equal to Kx, right? What is F equals Kx? This is the force is equal to K, which is the constant. So if this was a spring, this would be like the spring constant. And X is the deformation or the displacement of that spring. This is what we're going to use in part of the derivation that we're going to go over today. The next formula we need to remember is the formula for stress and how it relates to strain. And this is in the linear elastic region of our stress-strain diagram, right? So we have stress is equal to E, which is the modulus of elasticity, or we also call this Young's modulus, times the strain, epsilon. Okay. And then the last formula that's going to be helpful in this small derivation that we're going to do is strain, epsilon, equals the change in length of the member when subjected to an axial load divided by the original length of the member. Okay. So what we're going to do now is we're going to use these formulas and kind of construct the formula that we use when we have an axially loaded system. Okay. So let's move down a little bit right here. And let's just quickly draw a bar, okay? I'm going to draw this interesting shape here with this variable cross-section, just so we can kind of remember how this formula comes to be for a bar that maybe doesn't have a uniform cross-section, right? Or uniform loading, okay? Let's say we have some force P1 pulling on the bar in this direction. We have some forces here. And then we have some force P2 pulling in the opposite direction. I'm going to define my X to start from this point here. Okay. And we have some initial length of this bar. L. Okay. And if I were to pull on this bar, let's say we have some deformation that occurs, right? So we get some deformation. This bar, as we're pulling, kind of stretches like this. And this deformation we're going to call delta L. Or we can also call this little delta, lowercase delta, like this. Okay. Now, this bar, we're going to say that this bar deforms uniformly. Bar deforms uniformly. Okay. What we're going to do now is we're going to derive an equation to determine the elastic displacement of a member that's subjected to an axial load. And just so you remember, what is an axial load? This is the axial load. It's a load that's pulling along that longitudinal axis of the bar. What do we do to figure out this formula? You all remember, hope you all remember the method of sections. Okay. So what a method of sections is going to help us do is we're going to isolate a teeny tiny section of this element, okay? We're going to isolate a little section here. And when I do that, this little section, I'm going to kind of blow it up right here. Right? And of course, this little section has its own little deformation that's happening when we pull with that axial load P. And at this point, we don't necessarily know what that load is. I'm just going to put it some function of X starting from that starting point, right? Some function of X. And I'm going to say that I don't know what the cross-sectional area is, so It's some very function of x as well. It depends on where we are. That is the cross-sectional area. Okay. And then that P of x is that internal axial force as a function of x. And then this little part that we've pulled here is going to be the change in our displacement, d delta. And we don't know. We're just isolating this little teeny tiny section. We're going to call this delta x. I'm sorry, actually, let's use dx, that little differential element, dx. Okay. So now what we're going to do, we've kind of set this up to be derived for any cross-section or like a changing cross-section, changing load. Let's kind of go with this and then we'll kind of simplify the problem, okay? So now what we have is we're going to use these three formulas, Hooke's law, stress, and strain, to come up with a formula where we can relate, right? What are we relating again? We want to relate the elastic displacement of this bar with that axial load. Basically, let's come back here real quick. Let's figure out what we're doing. We want to know how much has this bar moved as a function of the load I'm pulling with. So I have this pencil in my hand. I'm pulling on the pencil from both ends, and I want to figure out an equation that tells me how much will this pencil deform if I'm pulling on the pencil with both ends. That's it. That's all we're trying to do here. Okay? So back to our equation that we're deriving. We know that stress is equal to force divided by area, right? I'm going to write this up here. This is our basic definition of stress. Force per unit area. And if you didn't remember that, make sure to go back and check out the stress strain video. Okay? But stress is equal to force divided by area. So what's the force in this system right here? This is the system we're looking at, right? What's the force? The force is, that's right, P of x. Divided by, what's the area? A of x. Simple. Okay? Let's do the same thing with strain now. Epsilon is equal to, well, what's epsilon equal to? Change in length over original length, right? So what is epsilon for this little differential element? Well, what's the change in length? It's d delta. What is the original length of the element? Dx. Okay? We're going to assume that this behaves elastically, which means we're allowed to use Hooke's law. So we can say that stress is equal to the modulus of elasticity. Let's say that we don't know it's a uniform modulus of elasticity, so as it changes as a function of x, multiplied by the strain. Okay? And now let's put everything together into one formula. We have stress P of x over A of x is equal to modulus of elasticity as a function of x times d delta dx. Okay? And now what do we do when we have a little differential element? We integrate. We integrate over the length, right? Okay? So, actually, before we integrate, let me simplify this. Let's move over this d delta. Because remember, we're trying to solve for that elastic displacement. So let's put it on one side. Then we get P of x on one side, dx divided by A of x. Now this looks a little bit better. Now let's integrate. Take the integral, right? And what are we integrating over? The entire length of the element, because we had isolated a little teeny tiny differential element. But really, we want this over the whole length of the system, right? So we're going to integrate over the whole length of the system. And what is our goal here? What is the goal? We want to solve for delta. That's the goal here. Well, let's just take a step back and make sure we know what this is. What is delta? I hope you said it's the displacement, right? This is the relative displacement of the bar. So back to our example, this pencil. What is delta? How much that bar is moving when I pull. That's it. It's just a measure. Right? In the lab, you would pull on something and you'd measure that delta with a ruler. That's all. We're just deriving a formula to solve for that. Delta is relative displacement. What is L? That's the original length of the member. What is P of x? I'm going to write a really important word right here. P of x is the internal axial force. I'm going to capitalize this. Right? I always like to remember this. Stress is something you feel when you're stressed out, so it's always inside. You always use the internal forces when you're calculating stress. Internal, okay? Never external. You're using the internal forces when calculating stress. Okay, moving along now. What do we have? We have two more things to define. We have, I'm going to continue right here, A of x, cross-sectional area. Okay, and E of x stands for the modulus of elasticity. Or Young's modulus, either one, same thing. Okay, so now what we're going to do is we're going to simplify this. This was just for the most general of cases in case we don't have a uniform cross-section or we don't have a uniform load, right? But typically in engineering problems, or a lot of the time, we do have a uniform cross-section and we do have uniform loading. So we're going to make our lives a little easier, and we're going to take this fancy looking bar and make it into a really simple bar. It looks like this, right? Uniform cross-section. And we're going to pull on this bar with a uniform load. Instead of P of x, we're going to call this P. So imagine this is our uniform bar. This is one P. This is another P. And we pull on this bar. And this bar, or this pencil in my case, right, has some length, initial length, L. Okay. And when we pull on this pencil, this bar, it's going to deform. It'll have some deformation, and we're going to call this deformation delta. Okay. We're going to start measuring from this point, x. Okay. And just to remember, what we're doing here is we're saying this is constant load, and we're saying this is constant area, constant cross-sectional area. So what happens here, if it's constant load, our P of x becomes just P. And if it's constant area, our A of x becomes just A, right? So I'm going to rewrite now this equation here. I'm going to rewrite this for our new case. And I get delta equals PL over AE. This should be a familiar formula, or I hope, right? And let's say you have multiple loads. All you have to do is say, well, then delta is equal to the sum of all the P's divided by the lengths which they act over the area times the modulus of elasticity of that section. And this is our function that relates the load to the elastic deformation. Easy, right? Okay. Now what we're going to do is we're going to go over an example, okay? And let's start by reading through this example. So we have a rigid beam that rests on two short posts, AC and BD. AC is steel and has a diameter of 20 millimeters, and BD is aluminum and has a diameter of 40 millimeters. Determine the displacement of point F on AB if a vertical load of 90 kilonewtons is applied over this point. Take the modulus of elasticity of the steel post to be 200 gigapascals and the modulus of elasticity of the aluminum post to be 70 gigapascals. All right, so what are we looking for? Let's summarize what we're looking for here. We're looking for displacement, specifically at point F, right here. Okay. One key piece of information is that this beam is rigid. What does that tell us? We have uniform displacement. Rigid means uniform displacement. Okay. All right. Let's start with post AC, okay? I'm just going to start by writing down this formula. Let me put it up here in the top corner. Delta equals PL over AE, okay? Let's start with number 1, post AC. What's the formula? Displacement for A is equal to the force, that axial force for AC, length of AC, divided by the area of AC, modulus of elasticity of steel because the post AC is steel. Number 2, for post BD, delta B is equal to the axial force at BD, the length of BD, divided by the area of BD times the modulus of elasticity of aluminum. Now let's look into this. What information do we already have to fill these equations? Do we have the length of AC? Yep, we do, 300 millimeters. Do we have the area of AC? Yes, we do. It's given in, the diameter is given, right? So that means we have the area. We have the modulus of elasticity for steel and aluminum. Same thing for BD. We have the length, we have the area, we have the modulus of elasticity. All we're missing is PAC and PBD. Okay, so let's now figure out what those P values are if we have that 90, right? We have the 90 kilonewton load. Let's break all of this up and see if we can figure out what the P values are. So what I'm going to do is I'm going to come down here and I'm going to take this frame and I'm going to explode it, which means I'm going to kind of expose all of those forces inside so we can see what we're working with here. Okay. So let's draw our top member and then let's draw our bottom member, our bottom post. Okay. Now, we have point CA or AB and then CD on the bottom. So we have A, B, C, D. I'm just going to kind of draw them far away so there's room to draw the other things that I want to draw on here. Okay. Let's start with this 90 kilonewton load, right? So we have a 90 kilonewton load that was given in the problem. Okay. Well, we also have, right, we have at AB, we have connections, right? So we have to have some force. Let's say we have an AY. That means we have an equal and opposite force acting on member AC, right? And since this is an axially loaded member, we don't need to worry about any other forces in any other direction except for the forces that act in the axial direction. So that means we also have AY that acts in this direction for equal and opposite, right? This is for equilibrium purposes. Well, we can do the same thing here. We would have a BY equal and opposite BY equal and opposite BY so that this system stays in equilibrium, right? If that's the case, now we can use this information. Let me put the dimensions on the top member here. So we had 200 and 400 millimeters. So we have 200 millimeters, 400 millimeters. What can we do to figure out AY and BY? We can use our equations of equilibrium, and we can sum moments about point A, set everything equal to 0, say counterclockwise is positive, and we can say that BY times a moment arm of 600 millimeters minus 90 times a moment arm of 200 millimeters. I'm doing equations of equilibrium for this right here. That's what this equation refers to, just so we are very clear. If I do that, I get BY equals 30. Okay? How can I get AY? I just subtract 90. They have to add up to 90. That means I'm left with 60. Okay, so actually, coming back here, I now have PAC and PBD, right? So let's come back here. What is the axial? Let me put this in highlighted section here. This here is post AC. This is post BD. What now is the axial load on AC? It's AY, 60 kilonewtons. What is the axial load on BD? It's BY, 30 kilonewtons. Okay, now I can go ahead and plug in displacement at point A. I'm going to use negative 60 because why? It's in compression. It's being pushed instead of pulled. How do I know it's in compression? Well, look at the direction of the arrows. You have one arrow pushing in this direction, one arrow pushing in this direction, compressing the member. It's getting shorter, not longer. If it's getting shorter, I need to put a negative here. Negative 60 times 10 to the 3 newtons. I'm going to put this in newtons. What's the length of the member? 0.3 meters. Divided by what's the area? Well, I have the diameter, so pi, half the diameter, which is radius squared. Gigapascals, I'm going to change to pascals. Pascals are newtons per meter squared. And I'm left with 0.286 millimeters. This is negative, or I can just show you that it's going down. It's getting shorter. Okay, let's do the same thing. Displacement at point B. Negative, also in compression. I'm putting everything in the most basic units. Same initial length of the member. Pi times 0.02 squared times 70 times 10 to the 9 pascals, which are newton per meter squared, and I get 0.102 millimeters, also negative, so going down. Am I done here? Not quite, because the problem asked for the displacement at point F, and I have the displacement at point A and B. So how do I now translate this to the displacement at point F? I have to come back here and remember that this is developed for a rigid beam, which means uniform displacement. So I can use a simple trick to figure out the displacement at any point on that bar. I'm going to come down here and show you what that trick is. So what I'm going to do is I'm going to copy a little portion of this diagram. I'm going to paste it down here for us to work with. Expand it a little bit, okay? So what I'm going to do is this. I know that point A, has moved down from its initial position, how much? 0.286 meters. So point A is now here, 0.286 meters down, right? I know that point B has moved 0.102 millimeters. I'm sorry, meters, 102 millimeters. So, okay. Now, that means, well, actually first before I tell you what we want, let's draw this. That means that if A is now down here, I'm going to put A new, and B is down here, B new, and I have to connect these because the member is rigid. It uniformly displaces, right? Displaces uniformly. That means my new F is moved down here to this point. And that's what I'm looking for now, right? All I have to do is use similar triangles now, okay? Let me show you the triangle. So I know that from here to here, right? From here to here is 102. That means that I can get this distance by saying 0.286 minus 0.102, and I'm left with 0.184. So if I were to redraw this triangle to show you, oops, there we go. I would have one side with 0.184. I would have the top of 400, right? And what I can do now is I can say, well, I'm looking for, sorry, not 400 there. What 400 am I talking about? I'm looking for this length, and this is 400. This is in meters. This is 200. And I'm looking for this right here. What am I going to call this? I'm going to call this delta F. Let me set up similar triangles. I can say that 0.184 is to the full length as that small portion, delta F, is to just 400. What did I just do? I set up similar triangles this big triangle to this little triangle. And what I can do now is I can solve for delta F, which is equal to 0.255. And let's check this because we're engineers and we always need to make sure our work makes sense. Delta F has to be in between delta B and delta A. It is, right? It's more than 0.102 and it's less than 0.286. It looks like we did it right. That is the displacement at point F. So now, the last step is something you're going to do on your own. You're going to try this practice problem. Okay? Similar concept, so I hope you can apply what you've learned today in this video to solving this practice problem. Again, I'm Dr. Munji, and I hope you learned something today that helped you understand axial load and how to relate axial load to axial deformation.